Mid-sem like exam?
Yeah, so currently it'll just the way that I've put things up on the website. There's going to be weekly homework, right? Assignments and a final exam. Okay, and there's not going to be a mid-sem exam at the moment. Okay, so but yeah, I mean, I personally don't like exams so much, but if some of you really want a midterm exam, we can have one. But it's since it's an elective course, it's up to you to sort of try to keep up and make progress and sort of keep up with the material being taught and sort of and I assume you all are interested in the subject, so just doing the weekly assignments should be fine. Okay, and then of course you can let me know and keep email me whenever things that you want to discuss or questions, right? Um, yeah, some of these things we'll kind of formalize perhaps and kind of have some solution for as the course progresses, like having some kind of online office hours or things like that. Okay, so all right, okay. All right, so any other questions before we start off with the material?
A small fund. Will you have a project or like a written final exam?
No, it will be a written final exam. Yeah.
Okay.
Yeah. So I guess the last time we taught this course, we had projects, but not this time, right? And it's I mean, we'll figure those things out later, but the exact mechanics of how it'll happen. It'll probably be take-home exams. Okay, so but we'll figure those things out. Right. But yeah, so the evaluation part of it is somewhat, sort of secondary. I've always considered it secondary. It's the most important thing is to, learn, the material. Okay, so I hope that you put in your efforts towards that. Okay. All right. Okay. So let me also turn off the video because I can't see any of you, and it'll my video might be a distraction, perhaps. Okay. All right. So I hope all of you can see the screen. If not, let me know. So we've kind of fixed certain things now. So we've decided on the new timings for the course. It'll be from Monday, Wednesday, Friday, 3 to 4, and I've already told you about this. So let me just draw a line here. So anyway, so right. So this course is about manifolds, right? That's the first thing in the course title, and manifolds are kind of essential to geometry. They are like like integers in number theory. One can't imagine number theory without integers, and it's the same thing for geometry. Okay, so and if sort of manifolds are central to geometry, so Lie groups are in fact sort of central to many parts of mathematics. Okay, so it's connected with geometry because Lie groups are also manifolds in their own right. Okay, and it's connected with algebra, of course, because it's a group. Okay, and there are other courses in the department about more algebraic aspects of Lie groups and Lie algebras, like so this appear in representation theory, for instance, and things like that. Okay, so there's an algebraic kind of connection here. So maybe I should do this. interplay, which we won't get into this course, but it's, you know, some other courses might be. And there's also a connection with analysis. Those who kind of are interested in analysis, the Lie groups come up in harmonic analysis. Okay, so and this is also a subject that is sort of well represented in our department, and some of you might be interested in such things. So in any case, there's this connection. There's also actually a connection. I mentioned number theory earlier, but there's a connection with number theory. Also, there's, I mean, in modern number theory, there's some sort of conjectural programs. There's this Langlands program, things like that. These are sort of very deep conjectures that relate, you know, various representations of Lie groups on one side, and sort of number theory topics in number theory on the other. Okay, so there's also a relation here, which again, I mean, this is kind of also quite advanced, and sort of maybe some of the number theorists in our department, Radhika and so on, they would be sort of more familiar with this aspect. So, but what in our course, we'll be sort of focusing on this part of things, as the title of the course suggests, and for some part of the course at least, I mean, so these manifolds will, I mean, so we'll talk about differentiable manifolds, and where Lie groups are some kind of an example of it. Okay, but hopefully we'll get to sort of proving things about Lie groups at the end, using all that we learned about. Okay, so here are some of the topics we aim to cover. So so there's always going to be some sort of basic stuff about manifolds and Lie groups, which I have not sort of listed here, but along the way, I mean, we'll be seeing things like tensors and tensor fields and differential forms and various things you can do to differential forms, like take exterior derivatives and things like that. You might have seen some of this already in, you know, calculus and several variables in Rn, but we'll be doing all these in manifolds, including integration on manifolds. This is something that you would definitely have seen in Rn and Stokes' theorem. So these all have versions in manifolds. So this is sort of, perhaps this part is just basically calculus and manifolds kind of thing, right? So that's the, and then there is also things like vector fields and their flows, Lie brackets, vector fields, and all that kind of thing. And sort of Frobenius's theorem is going to be an important sort of part where we talk of, you know, distributions, and then sort of prove Frobenius's theorem on integrability, and then all these topics, you know, get sort of are useful, sort of get combined, get used in the proof of the Lie correspondence. This is something that I want to get to. This is some theorem about Lie groups. This is a correspondence between Lie groups and Lie algebras, and this is a very fundamental theorem. It's called the fundamental theorem of Lie. Okay, of Lie theory. This is sort of the basic results, and eventually, so one of the goals of this course is to get to that, is to get to the proof of the Lie correspondence. Okay. I should also add, maybe I should add here, I want to get to also talk a bit, since we'd be doing differential forms, etc. I'll be wanting to also talk about DRAM cohomology, and maybe if time permits, let's hope it does, we'll go to Poincare duality. Okay, so things like that. Yeah, and for this last topic, it helps if you know, sort of, you're familiar with, let's say, singular cohomology theory or something like that. And this is covered in MA 332, but it's not essential. I mean, you can probably appreciate this DRAM cohomology better if you already have a little bit of an idea of homology and cohomology, but you can learn it here as well for the first time. It's fine. Okay. All right. So that's the rough plan. Yes.
In this course, will we be going into the correspondence between singular cohomology and DRAM cohomology and the DRAM theorem and all?
We might not have time to actually do DRAM theorem, but let's see. I mean, it depends. If we have time, we'll talk about that. Okay, but certainly, you know, sort of some of the books that I've listed in the course website. There's, in particular, this you know, Lee's book on smooth manifolds, not you know, LIE Lee, and not the Lee of Lee groups, but LEE. Anyway, so this the Lee's book does get to things like DRAM theorem, etc. So in case we don't get to it, I mean, I think it will be you know, sort of possible for a student to easily get to it after the course. Okay, so it's sort of it will be probably, if the course, you know, runs a little longer, then we could have covered it, that sort of thing. Okay, so but in my experience last time I taught the course, I wasn't able to get to DRAM's theorem proper, but maybe this time we'll go fast. It depends. Okay, so yeah. Okay, all right. Anyway, okay, so that's the plan, right? So yeah, I'm also kind of figuring out how exactly to do this writing. So this is sort of something I'm experimenting with. I mean, so I'm going to sometimes do things like this, where sort of it's somewhere in between having slides and having a blackboard, right? So where part of the material is there, so you can have at a glance maybe what's going to come, and then I fill things in. Okay, so in any case, let's begin by before we get to differentiable manifolds. Let me start by telling you about topological manifolds, okay, which is sort of an even more basic object, all right? And maybe you've come across this already in course in topology or something. Okay, so what's a topological manifold M? Well, it's a topological space that is A. It is Hausdorff, or the first property that we want is Hausdorff. And if you remember, it's that you can separate points by open sets. Okay, and the second property is it's second countable, and this means that there is a countable basis for this topology. And so these are sort of terms you might have come across in your point set topology course, and the second countability might seem a little bit odd at the moment, but you'll see that it's a useful thing to assume. We'll come to why these are desirable, why these two properties are desirable. But the most important property, and this is sort of the characterizing property, this is for a topological, for being some topological space being a manifold, is the fact that it's locally Euclidean. Okay, so let me explain what that is also. So this is going to be sort of the defining property, really. It's locally Euclidean. And what this means is that each point X in M has a neighborhood. I'm going to abbreviate neighborhood like this, okay, which is homeomorphic to an open subset of some Euclidean space, let's say Rn. Okay, so so in other words, let's have a picture. So if here's my manifold M, here's a point X. So there's going to be a neighborhood U of X, and there's going to be a homeomorphism of U with some open set, let's call it phi of U, sitting inside Rn. So here we've kind of drawn these two axes. It's like an R2, like the surface of this tablet, but in general it could be Rn. Okay, and so let me just sort of say so let me call this neighborhood U here homeomorphic open subset. So that is, there exists a homeomorphism phi from U to phi of U, which is a subset of Rn, and phi of U is open. Right, that's the sort of, not in words, but you want to write things down and give things name. That's how you say it. Okay, and then I'm going to often, refer to this pair U phi, and this would be called the pair U phi. There's a coordinate chart. And phi inverse is a parametrization, sort of a local parametrization around the point X. Because a phi inverse, remember, phi is a homeomorphism, so you can sort of go backwards as well, and that's going to be phi inverse, and that's so that's a local parametrization. So locally Euclidean just means that locally around every point your manifold looks like it's part of Rn. All right, so there's a neighborhood which is indistinguishable from Rn, and so this phi inverse is sort of giving coordinates to points in a neighborhood of the point X. Okay, so sort of you can call them, if you have coordinates, sort of x1 to xn in Rn. You can use this phi inverse to talk about those points on M instead of in the Rn. Okay, so this is some back and forth we'll be doing a lot. We'll be talking of neighborhoods of points on a manifold as if they were open sets in Rn. Okay, and here in this whole discussion there was this integer n that I kind of wrote down. This, so if you have the same integer n in all points, that's the dimension of the manifold. Okay, so so let me actually remark that very often we'll be talking of connected manifolds. So, and if M is connected, this is another notion in point set topology that you would have come across. So then the dimension n is well defined. It can't change from one point to another because you have something called the invariance of domain. Because of the invariance of domain. This is a theorem which says that open sets in Rn, Rn and Rm cannot be homeomorphic to each other if n and m are different, right? So so if you have a connected manifold, then it turns out that once you have some part which is locally like Rn, sort of every other point would be also locally Rn. So, if it's a manifold and which is connected. Otherwise, of course, you can just take disjoint unions of one manifold of dimension n and another manifold dimension m. That's not going to be connected though, but it's still going to be manifold. So sometimes we'll when we talk of manifolds, if we say we can sometimes say of dimension n, and some places would also assume that it is connected, but we will keep the connected assumption we'll probably also, sort of implicitly assume connected many times. But so that's why I've kept it as the 0th condition. But we'll see how it goes. And a lot of the things actually go through, if it's not connected, you just do things for every connected component. Okay, and so you're fine there. Okay, so it's not an essential assumption. Yeah, but what are essential are these three: Hausdorff, second countable, and of course the locally Euclidean assumption. All right. Okay, so that's the definition. By the way, if you have any questions, you feel free, as I said, to stop me and ask. So here are some examples. Okay, so the 0th example is Rn itself. Okay, so that's certainly locally Euclidean. It's the Euclidean space itself. And in fact, you can also take any open set in Rn. Right, so that's also a manifold. Any open set in Rn is a manifold. Here, the chart that you want, remember that you want these homeomorphisms locally at every point. So if you are already an open set in Rn, then this homeomorphism phi would just be the inclusion map, or the identity map, or whatever you want to call it. The inclusion map is probably the more accurate description. Okay, so these are some basic examples. Another example is a graph of a continuous function. Okay, so let me say what that means. So if you have, suppose I start with an open set in Rn, and you start with a continuous function. Let's make it. Maybe I'll make it value in R, but I mean, it's a function, but you can actually also talk of continuous maps from U to Rm. But so you start with a continuous function, and you consider the graph. Okay, so the manifold would be the graph, which is all the points x comma f of x, where x is in U, and that's going to be some subset of Rn plus 1. Okay. Of course, if we had here, instead of 1 here, if we had, let's say, Rm, then it would be sort of n plus m instead. Okay, so but in any case, this is a graph, and you consider the subset with the subspace topology. Now, this is certainly since it's a subspace of Euclidean space, it's going to be Hausdorff and second countable. Okay, so that's automatic. First, let me draw a picture of what this whole thing is about. So this is sort of let's talk about the case where your n is 2. Okay, so this is this plane is R2, and your U is sitting there as open set, and so the graph would look like some subset of R3, right? And it's going to be Hausdorff and second countable, as I just said. So this is going to be Rm, and it's also going to be locally Euclidean, because if you look at a point X, if you take a neighborhood of it, then you get a chart which is just nothing but the projection down to R2. Okay, so the projection to Rn in general. So that forgets about this last factor f of x, and just records this x. So it's a map to Rn that takes this to x, right? So that's the projection to Rn, and these are sort of at every point, the neighborhood at every point. These will give you, well, actually, sort of even globally, these give you the coordinate. These provide coordinates charts. So these provide the charts. Okay, so that's another sort of easy example. The first sort of non-trivial example of topological manifold, or something that's familiar to all of you, these are spheres. Sn, the n-dimensional sphere, is all the set of points in Rn plus 1, which have norm 1. So, so this is my definition of the norm, the usual Euclidean distance. And this is a subset of Rn plus 1, right? So it's again going to be Hausdorff and second countable. And here it's not really a graph, as you know of over any of these coordinate planes, at least. But you can provide charts by breaking it up into sort of different pieces. So so what are the charts here? What are the coordinate charts here? So one way of defining coordinate charts is for each. So here's a picture of the sphere. First of all, let me draw that first. And so somehow so maybe so this equatorial circle lies perhaps on one of the coordinate planes. All right. And then you have this some kind of upper hemisphere and a lower hemisphere. This, of course, is dimension. Well, it's a two-dimensional sphere that I've drawn here because I can't draw higher dimensions, but the same kind of you can imagine that the same happens in any dimension. So let me say what happens in any dimension. So for each, so one way of giving charts is for each I from 1 to n plus 1, we define charts u plus and u minus. So let's say, so these are going to be the open sets in the manifold, and these are x1 to xn plus 1, all the points that have the ith coordinate positive. So here, I mean, in the picture that I drew, this would be like u3 plus, and this lower shaded region, maybe I should shade it somewhat differently. This would be u3 minus. Okay, so ui minus is again a subset of Sn, would be a set of points where the ith coordinate is negative. Okay, and since there are n plus 1 such coordinates, there are, n, total is total number of open sets of defined is twice n plus 1. Okay, so 2n plus 2 of these, and each of these are graphs, right? So let me, I guess I've run out of space, so let me move this below. Yeah, so each of these are graphs. So so you can define coordinate charts, the phi i's corresponding to these, plus or minus, to so actually unit balls in Rn, by taking x1 to xn plus 1 to just projection to that part of, to that coordinate plane. So you kind of, you throw out this the ith coordinate. So this hat, as usual, sort of indicates that you sort of you throw it out, right? So okay, so and these are homeomorphisms. Okay, so you can, so these are, let me just say this by this twiddle. So these are the charts, right? And these 2n plus 2 charts, they cover Sn, right? So every point belongs to one of these charts. So every point has a neighborhood which is homeomorphic to some open set in Rn. So that's the locally Euclidean part of the definition of a topological manifold. Okay, so by the way, so here you had 2n plus 2 charts, but you can also do with lesser number of charts. So what do you think is the minimum number of charts that you need for defining a manifold describing a manifold on a structure on Sn? I mean, so for showing that Sn is a manifold, rather.
Is it 2?
Yes, that's right. Yeah, so you might also be familiar with, sort of, yeah, that's right, the stereographic projection, where you look at the North Pole and the South Pole, and everything in the complement of the North Pole you can identify with one chart, and the complement of the South Pole you can identify with another chart, right? And you can't quite do it one, right? So in this previous example, the graph of a continuous function, you just needed basically one chart that covers the whole thing, right? But here you can't do it with one, and I leave that to you to ponder about. Anyway, there are various ways of covering Sn with charts, and this I've described one of them. And that's enough for us. That's for now. I mean, so you know now that it's a manifold. But I guess you already did know that. Anyway, so the next example of manifold is real projective spaces. So these are also denoted RPN. So that's it's a space of lines in Rn plus 1. So it's you take Rn plus 1 minus the origin, and you impose this equivalence relation. Okay, so where so any 2 points lie on the define the same point. I mean, so the equivalence relation is if they are multiples of each other. Okay, so if lambda is not equal to 0, lambda belongs to R. Okay, so everything somehow lying on the same line is 1 point. So here, sort of, let's say this is the origin. So these 2 lines that I've drawn are actually 2 points in RP, RPN. I mean, here, of course, I'm constrained by dimension. I mean, this is probably, I'm just drawing RP2 or RP1 here, rather, because this, I mean, the surface of my tablet is R2. But you can imagine the same thing goes on in higher dimensions. And so you have these lines, and so the space of these lines is the real projective space. Okay, it's going to be an exercise in the first problem set that I'll try to put out by Friday. Oops, I think so. First problem set that this. So maybe I should use a different color here as an exercise. Is that this is actually is our Hausdorff and second countable. Now it's not exactly a subset of our Euclidean space. It's not automatic, perhaps, but it's not too difficult. I mean, this is defined as a quotient space. It's the quotient topology. But this is an exercise not hard to check. All right, and so again, so this one is also locally Euclidean. That's the most important property of a manifold, as I mentioned. And so here you can provide the following charts. So for each I from 1 to n plus 1, let me move these down to give myself more space. For each I from 1 to n plus 1, so you can you define ui to be all those equivalence classes of these points in Rn plus 1. I denote those by these square brackets, where xi is not equal to 0. So xi is non-zero. So these are actually sort of open sets in RPN, because these are open, and that's not hard to check. I mean, it's open. There are sort of images of open sets under the quotient map, right? Open sets in Rn plus 1. Okay, and so anyway, so as sort of these are the sort of my charts that will cover RPN, and each of these you can define a homeomorphism to Rn by sending x1 to xn plus 1, this equivalence class to x1 divided. Remember, the xith coordinate is non-zero, so you're allowed to divide by it, and so you kind of so you divide all these by xi, and you throw out that xi by xi. That's not included, so it's because you need to have n sort of terms here, right? So anyway, these are, I mean, the details are not hard to check. That these are actually going to be homeomorphisms. It's first of all, it's well defined, right? So whenever you are trying to define something, some map on a quotient space, you need, so there are these brackets here. These are equivalence classes. So you need to check that it's well defined. So you can actually check that. So let me just mention that. So you can check these. So these maps phi I are well defined and continuous and homeomorphisms. Continuous is sort of automatic. You're just basically dividing by something else. And these are homeomorphisms. Okay, so and why is this? Well, it's because you can define, I mean, this last thing is because you can define inverse, right? So if you're the inverse of a point in Rn, so U1, let's call it U1 to Un, you can define it to be the equivalence class of U1 to Un, where you throw in 1 at the ith place. Okay, so it's like Ui minus 1, 1, Ui plus 1, Un. Okay, so this is this equivalence class, and you can check that these maps that we've defined here is actually the inverse of the map phi I. Okay, so anyway, so this is something that this is another example. Okay, I've again run out of space, so let me push these down. And this is actually a different example than spheres, right? So these real projective spaces are different except when n is equal to 1, right? RP1 is nothing but S1. This is actually sort of the same. These are homeomorphic spaces, okay? But in general, these are different. So these gives you lots of examples. And you can also make others by taking products, okay? And I mean, so this is something that I won't get into details of, but it's sort of something that you would expect if M is an M manifold. So when I say M manifold, means a manifold dimension M, little m, and capital N is an N manifold. Then you can define a manifold's, I mean, the product space also becomes a manifold. It's easy to see. I mean, the charts become the products of the charts of M and charts of N, and this product is an M plus N manifold. So if you take products of these spheres and these real projective spaces, etc., you get lots of examples. And one example is the N torus. This will appear, I'm sure, several times in this course. As the product of S1 n times, right? So that's an example of a product. Okay. Before I mention well, okay. So let me sort of skip non-examples. I mean, so I wanted to give a silly example of a non-example, which is sort of something which is locally. Well, since I've kind of defined things to be Hausdorff, there are things which are locally Euclidean but not Hausdorff, okay? And there are things which are locally Euclidean but not second countable. Those things are non-examples. And so there's something called the line with a doubled origin. You might have come across that in the in your points at topology course, that's going to be that's not Hausdorff, so it's not a manifold by definition. But it turns out it is locally Euclidean. It looks like a line anywhere. I mean, it looks like an interval. Every point has a neighborhood, which is an interval. Okay. So anyway, so this is just to point out that we want Hausdorff, so that's going to be sort of important for us.
Hello.
Yes. Hello.
How do you look at the? I mean, you are saying that it is a double origin, right? Double origin line.
Yeah, that's right.
How do you characterize a neighborhood around 0? I mean, it's a line which is attached at 0. Two lines which are attached to 0, right?
Yeah, that's right. Yes, that's the line with doubled origin. Yeah. So you can't. I mean, it turns out it's not Hausdorff, right? You can talk of open sets, of course, right? You can talk of open sets. You can talk of neighborhoods of points, etc., etc.
It going to be a star-shaped. I mean, and except something. I mean,
Yeah. So okay. So maybe since you're asking, so what is a line with doubled origin? So it's something like this. So you kind of you take two copies of the real line, right? And you declare that so that's your sort of starting thing, and then you have declare that so something. So let's call them something. So maybe I'll call the space. So let's just call the space X.
I'm sorry, sir. I didn't see that it is non-example. So it is actually basically the quotient topology you are giving, right?
Yeah, that's right. So if you take, let's call the space R cross plus 1 and minus 1. So this is some subset of R2, if you like. So this is at height plus 1. This is at height minus 1. And then you define the quotient space where t comma minus 1 is identified with t plus 1. So every point is identified with, so the corresponding thing here. So except the origin, right? So this is for t not equal to 0. Okay, so somehow sort of everything collapses to a line except the origin is sort of, there's a doubled origin here. Okay, so and that turns out it's locally Euclidean, but it's not Hausdorff. So let me say, but it's locally Euclidean. So it satisfies one of the properties and not the others, and you can come up with other examples where, so the three properties I listed. I mean, so it satisfies two of them, but not the other, and things like that. So that is sort of, I leave to you. Okay, but there are many more examples of manifolds. So does anyone have a favorite example of a topological manifold? I mean, apart is not one of these. I'm sure we'll come across many of them, but
I mean GLN.
Yeah, that's right. Okay, good, great. Yes, I mean, yeah, if you're here for Lie, differentiable manifolds and Lie groups course, then of course, you've all these matrix groups, all these Lie groups that are also going to be manifolds, and so like orthogonal group, like the special linear group, etc., etc. So these are all going to be manifolds, and which are going to be important for us. Okay, so much for topological manifolds. So what we want to really get to are differentiable manifolds, right? So let's sort of define them. So maybe I won't define a smooth manifold in one go, but first let me define what a smooth atlas is. So by the way, I'm going to use these two words interchangeably, differentiable and smooth. Okay, so some people call them smooth manifolds. It's like these, the one of the books that I mentioned, listed on the course website. It's actually called Introduction to Smooth Manifolds or something like that. Okay, so but these two terms are used interchangeably, and I'll do the same. Okay, so the first thing that I want to define is like a differentiable. Let me just call it smooth. Sometimes it's also called C infinity. Okay, so infinitely many times differentiable. That's what smooth. would be for us. Okay, so for us, when we talk about differentiable manifolds, it will be all these infinitely many times differentiable. So first, let's define a smooth or C infinity atlas. Okay, this is a hyphen, by the way, so it's sort of dash. Atlas on a topological manifold. So we'll start with a topological manifold. That's going to be sort of the more basic object. Let's say of dimension n, so I'll call it an n manifold M. And what's a smooth atlas? Well, it's a collection of charts like we had before. So these coordinate charts, let's call them ui phi. So there are some index set. So when it's second countable, you can actually take this index set to be countable set. But let's not specify that or worry about it for the moment. So it's a collection of these charts, so that of course these cover these open sets UIs. They covers M, and each transition map, and I'll define what they are, is smooth. Okay, smooth of C infinity. And what's a transition map? Well, these are defined on overlaps of charts. Okay, so these are so the transition map. So let's say you have, maybe let me draw a picture. Okay, so I seem to have underestimated this kind of amount of space that I need. So let me say what a transition map first is a picture. So here's my topological manifold M, and suppose I have overlapping charts U, I, and Uj, and so they have these corresponding maps phi I and phi j, which are homeomorphisms to some open sets. And the part that's so let's call them overlaps here, and the part that's overlapping. So this maybe I should shade it something else. Maybe it's not too visible. Anyway, so there's some part is overlapping, so that maps here and that maps here, and so on these overlaps there is a transition map from one side to the other, right? So it's just because so this is the transition map. So this transition, what I call the transition map, is really this. It's defined on these overlaps, and you have a map from here to there because remember that phi i's and phi j's are homeomorphisms, so you can sort of go backwards. Phi I. So if you start off here, you can go backwards and go to this overlap region, and then map down again here by phi j. Okay, and so when you write it down, it's like phi j composed with phi I inverse. So you do phi I inverse first, and then phi j. And the overlapped regions you can describe as this, mapping to this. Okay, so that's the transition map. And so this, I want these, for any such pair of overlapping charts, to be a smooth or C infinity map. Okay, so infinitely many times differentiable. And this makes sense now because these are, sort of subsets of Rn, remember. Okay, so these domain and range for these transition maps are subsets of Rn. So you know what infinitely differentiable means. I might review this also in next time, perhaps, if any of you want to review a little bit of sort of calculus of several variables in Rn. Also, maybe it'll be I'll do that next time. But okay, so but that's what this smooth atlas means. And there are many examples because all of the examples I talked about, notably the spheres and real projective spaces, are smooth. Okay, so the charts we defined on Sn and Rpn define a smooth atlas. Okay, and I leave you to verify that these that these transition maps on the overlaps are indeed differentiable functions. Okay, and it's it's sort of easy to write down the expressions for those. Okay, and so let me not get into that at the moment. But let me just say that, I mean, so why we care? I mean, why aren't we just happy with a topological manifold? Why do we need this extra thing of requiring these transition maps to be smooth? So let me just sort of answer that with a remark that, so this, if you have a smooth atlas, so given a smooth atlas on M, we can make sense of saying something like f, the function on the manifold is smooth. Okay, so it allows us to define smooth functions. That's what I want to say. Okay, so it's sort of and a priori, I mean, if you talk of differentiability and smoothness, you only can do it for sort of open subsets of Rn, right? So like here, sort of something defined in an open subset of Rn, you can talk of being differentiable there. But if you have a smooth atlas on your topological manifold, you can also talk of smooth functions on that topological manifold. And this is because, well, how do you define something as smooth? Well, you can just require, you can sort of by requiring that if something is smooth, then sort of locally these maps at the level of charts are smooth. So so let me just write it down and then sort of look at the picture again. So maybe I'll draw another picture. Okay, so let me put this down again. Okay, so all right, so by requiring that these are smooth, well, what are these? Well, so remember, here's your manifold M, and what's a function fm to r? Well, it's just a map that assigns to every point some real number. But you can talk of when something is smooth at a point, you can define it at the level of charts, because you know that in the neighborhood of a point x, your manifold looks like an open set in Rn, right? And so if you look at this, let's say take ui and phi, and this is my phi of ui, and this phi is a homeomorphism, so you can go backwards and you can define this as a sort of locally, this map f at the level of charts defines a map from an open subset of Rn to R. Okay, here I'm assuming the manifold is n dimensional. So this is what's and now here, so something like this, you can talk of the smoothness of that map, because now your domain is an open set in Rn, your target is R, so there's no problem. Okay, so and so if you have a smooth atlas with this compatibility, these transition maps being smooth, it only makes sure that this notion is well defined, right? So you could have taken, for instance, so if you want to talk about smoothness around the point X, maybe you could have taken, some other, sort of chart uj containing X. But since you have a smooth atlas, and ui and uj's are all sort of differ by these smooth maps, these transition maps are smooth, then so f with this new, the other chart would also be a smooth at the point X. Okay, so this is sort of what's what's going on and why we need this definition. Okay, and the advantage with now having defined smooth maps would be that if you can do calculus on these manifolds as well. Okay, and that's what this the whole thing is about. Okay, and we'll see many sort of advantages of that and repercussions and so on. The whole sort of subject builds on that. Okay, so this is why we need this smooth, these atlas, these coordinate charts to be smooth, so to differ on their overlaps by smooth maps, but then you might, yes.
Yeah, so we had two charts. If we have two charts, since this transition map is smooth, our definition is consistent. So will the definition for the function f to be differentiable on a manifold? So but if we calculate the derivative of f in the one chart ui and the another chart uj, should they be same? I mean, do we expect it to be same?
Yeah, we'll talk about all that later. Yeah, that's right. I mean, so at least right now, the smoothness, that's a very good question. So at least the notion of smoothness is well defined if you have the smooth atlas. But it's not yet clear what happens to derivatives, right? How can you talk of derivatives and so on? So that's going to be coming up in the course. Okay, one of the first things that we do after all these basic definitions is going to talk of, well, can you talk of derivatives? Okay, that's a good question. Okay, we'll come to that. So, but first there's another worry that here, sort of had chosen a smooth atlas or given a smooth atlas, and so let's say on SN we've already sort of seen one way of defining some charts on SN, but maybe you can choose another way, like someone suggested, stereographic projection and so on. So you have to have a notion of compatibility of different atlases. Okay, so let me sort of mention what it is. So we say that two smooth atlases are compatible with each other if their union. So both of these are collections of coordinate charts, UI, phi. You can take the union, and the union is also a smooth atlas. So that, sort of, even if you add the new ones, the coordinate charts of the other atlas, you still get compatibility. Still the transition maps that you get are on the overlaps are smooth. Okay, so so this is a notion of compatible, and what you really care about is sort of smooth atlases up to this notion of compatibility. Okay, so you don't want to talk about sort of need to worry about how I define the smooth atlas on a topological manifold. If you define it in two different ways that are compatible with each other, then it's actually the same sort of same smooth manifold. Okay, and this is what now gives sort of finally we can sort of talk about the definition of a smooth, a differentiable, a C-infinity structure. Okay, and let me make space for that. And so this structure on a topological manifold, and this is going to be our smooth manifold. Okay, so this is going to be the definition of a smooth manifold. So on a topological manifold, M is also one succinct way to describe it is the maximal smooth atlas. What it means is that it's a maximal in the sense of inclusions. Okay, so it's sort of the there's no other smooth atlas which contains this, right? So this is sort of it contains it strictly. Okay, so another way of thinking about sort of equivalently or alternatively, let me mention both. So alternatively, it is alternatively, it is an equivalence class of compatible smooth atlases. So compatibility gives you an equivalence relation. So it is an equivalence class of that. Okay, so sort of if you have two atlases that are compatible with each other, then they define the same the same smooth structure. Okay, if they're not compatible with each other, then they are defined two different smooth structures. Okay, so that's what a smooth structure is, and as I said, I mean, so if you have a topological manifold with a smooth structure, then then M is said to be a differentiable manifold or a smooth manifold, a differentiable or smooth or C infinity sometimes manifold. Okay, so that's the definition of, sort of the one of the terms in the title of the course, right? And so let me just actually say a little bit more perhaps. So you can have, let's say, two smooth structures on R, because you can take one of the charts to be defined as a global chart. Okay, so I'm covering R with itself, and this is just the identity map, and you can have another chart which is something like x goes to x cubed. Okay, and then these charts is easy to check. These are not compatible. If you take the union of these two charts, then not quite compatible, because the cube root is not a differentiable function at x equal to 0, right? So that causes a problem about compatibility. Okay, so but these are still the same smooth manifold, because these structures are diffeomorphic. Okay, so let me sort of end with this last definition. So let me just say about the but R with these two structures, they give you smooth manifolds, but these are actually the same manifolds because these are diffeomorphic to each other. So these structures are diffeomorphic. This is the sort of notion of equal in the category of smooth manifolds, right? So the or equal or isomorphisms in the category of smooth manifolds. These structures are diffeomorphic to each other. And what's a diffeomorphism? Well, a diffeomorphism of two manifolds is defined. I mean, it's something what you expect. So two smooth manifolds, M and N. So smooth manifolds M and N are diffeomorphic if there exists a bijection M to N such that with F and so bijection is just at least set theoretically that's isomorphic, but then require both F and F inverse or smooth maps. Okay, and once again, if I want to define a smooth map, I have to sort of say what it is. So maybe let me add a, maybe since I've so maybe I'll just mention what a smooth map is over here. So I've talked about smooth functions, but I mean, so you can talk of smooth maps between two manifolds. So here you have F from M to N. You can define smooth at a point X. If you're locally at the level of charts, your map is smooth, right? So there is this chart U comma phi that maps to some phi of U here. This is some subset of, let's say, Rm. Okay, that's the dimension of capital M. And this X maps to F of X, and that has a neighborhood, let's call it V, and some chart psi, so that psi of V is some subset of Rn, right? So this, at the level of charts, you have this map that's basically well, it's phi inverse composed with F composed with psi, right? So that's the map, and you can talk of this being smooth. So this is smooth. So whenever you have this being satisfied, then you say that this map between manifolds is smooth. So you can talk of an equivalence of two manifolds being diffeomorphic. So this so when they're diffeomorphic, they're really the same smooth manifold, and that happens in this case when you have these two smooth structures on R. So it turns out, so this is sort of an exercise, perhaps. So maybe I'll. Let me say, so you can construct a bijection between these two smooth structures, these two smooth manifolds, is actually a diffeomorphism. Okay, so that's about these definitions. Now let me sort of conclude with a few facts. It turns out that Rn has a unique smooth structure up to diffeomorphism, except n equals 4, where it has infinitely many. This was a surprise at the time. This was it's followed from work of Friedman and Donaldson in the 1980s. Okay, so it turns out that if you look at other manifolds, S7 has different smooth structures, even up to diffeomorphism. Okay, so there are different smooth structures you can put on S7. The fact that there's 28 is probably due to Milner and Kerver, but the first, so Milner was the first who famously kind of discovered the fact that you can put different smooth structures, which are different even up to diffeomorphism, on the same topological manifold. Okay, and it turns out that S1, S2, these all have smooth structures up to dimension 6, except S4, and that's an open problem. It's called the smooth Poincaré conjecture. This is still unsolved, and it seems to be completely up in the air. Nobody has any idea. Okay, so it's whether S4 has different smooth structures that are not diffeomorphic to each other. Okay. So let me just mention that, sort of up to diffeomorphism. Okay, so that's an open problem. I would also mention maybe quickly a couple of other things. So first, I mean, there are topological manifolds without any smooth structure possible. You can't give it a smooth atlas at all. So smooth manifolds that do not have any smooth structure. This is sort of a surprise. Of course, these examples are higher dimensional. I think this is due to Kerver, 1960s, but that's not true in dimensions 1, 2, and 3. So in dimensions, this is why sort of low dimensional topology is sort of nicer in this aspect. So in dimensions 1, 2, and 3, any topological manifold has a smooth structure. In fact, has a unique one. Has a unique smooth structure. Okay, so anyway, so it's 5 o'clock now, so maybe I'll stop here. But if there are any questions, please unmute yourself and ask. I'll stop the recording.
Hello, sir.
Yeah, hi.